All right, welcome to the Explainer. Today, we are cracking open the engine that powers, well, pretty much all of modern AI. We're going to deconstruct the transformer, that brilliant architecture that since 2017 has totally changed the game. Let's dive in. So, you've probably used the tools, you've seen the headlines, but have you ever really stopped and wondered what's actually going on inside the brain of an AI? How do they really understand what we're saying and then generate language that sounds so human?
Well, for the most part, the answer is a single, game-changing idea called the transformer. But here's the thing, it's not some fixed, dusty blueprint. It's more like a collection of really smart solutions to some incredibly tough problems. It all started with a simple core idea, an encoder to understand stuff and a decoder to create stuff.
To really get why the transformer is such a big deal, we've got to look at the problems it had to solve first. And the very first one is a real head-scratcher. How does a machine, which just sees a bunch of words, understand that the order of those words is everything? You see, the magic ingredient in a transformer is this thing called self-attention. It lets every single word in a sentence look at every other word all at the same time. Super powerful, right? But it also creates a massive problem. By itself, it's order blind. It just sees a sentence as a jumble, like a bag of words. So to the model, the dog chased the cat and the cat chased the dog would look exactly the same. And yeah, that's a huge issue. The meaning is completely lost. So how do you fix that? Well, you basically give each word its own little GPS tag. They're technically called positional embeddings, and they're just little bits of extra info you stick onto each word that screams, hey, I'm in position number 1, or I'm in position number 3. The model absolutely needs this to have any hope of understanding grammar and context.
The first idea for this was pretty smart. It just added unique signals to each word right at the start. But the modern way of doing it, called rotary position embeddings, or ROPE, which you hear about all the time, is just so much more elegant. Instead of just tacking on a signal, ROPE actually rotates the data for each word based on its position. This means the model learns the relative distance between words directly as it's doing its calculations. It's way more effective, and that's why it's the standard in most major models today.
Okay, so problem 1, word order, is solved. But just as researchers started trying to build bigger and better models, 2 new Goliaths appeared on the horizon, threatening to stop all this progress dead in its tracks. Insane instability and just cripplingly slow speeds. So the first challenge is stability. When you stack dozens or even hundreds of these transformer layers on top of each other, the numbers flying around inside the network can just go wild. They can explode into infinity or shrink down to 0. Imagine trying to build a skyscraper, but every new floor you add randomly makes the floor below it 10 times bigger or 10 times smaller. The whole thing would just collapse, right? That is exactly what training a deep model is like without stabilization.
And a solution was this beautifully simple trick called layer normalization. Think of it like a regulator. At every single step, it looks at the numbers zipping by and just gently nudges them back into a nice, stable, predictable range. This one little change keeps everything from going haywire and makes training dramatically better. There's a newer, even faster version called RMS norm that you'll see a lot, but the core idea is the same. You gotta tame those numbers.
All right, challenge number 2 was all about speed, or really the lack of it. Remember how we said every word looks at every other word? That's the secret sauce, but man, is it expensive. The compute cost grows quadratically, n squared. So for a couple of sentences, it's fine. But what if you want to feed it an entire book or a huge chunk of code? The number of calculations becomes astronomical. It's just impossibly slow. This was a major wall. So to get around this wall, engineers got really clever. They came up with a whole bag of tricks to make attention more efficient. Instead of having every word look at everything, they limited its vision. With sliding window attention, a word only pays attention to its closest neighbors. With things like grouped query attention, or GQA, different parts of the model basically share notes to save on calculations. These clever shortcuts were the absolute key that unlocked the giant, long-context models we have today. All these different solutions really point to one thing. The transformer isn't some monolithic object. It's an adaptable blueprint. The original design was for translation, but it quickly evolved into this whole family tree of specialized models, each branch designed to do a different job really, really well. Yeah, think of it like a family of specialists. You've got the original, the encoder-decoder, which is perfect for taking something in, chewing on it, and spitting out something new, like translating English to French. Then you've got the analyst of the family, the encoder-only models like BERT, which are amazing at just reading text to understand and classify it. And then you have the star of the show these days, the generator, the decoder-only models like GPT. All they do is predict the next word over and over again. And that's exactly how your favorite chatbot works. And this right here is the big twist in the story. While those other architectures are still super useful, the most powerful, most famous models in the world today, they are almost all decoder only. It just turns out that the simple task of predicting the next word, when you do it at a massive scale with an insane amount of data, becomes this unbelievably powerful and general-purpose skill. You can throw almost any language task at it, and it can figure it out.
Okay, so we've taken a quick tour through the guts of the transformer. What's the big picture here? What are the crucial things you should really walk away with?
The main thing to remember is that the transformer isn't just a static diagram from 2017. It's a story of problem solving. It's about overcoming challenges like word order with rope and speed with GQA. It's a flexible family of architectures with different tools for different jobs. And honestly, it was those clever efficiency tricks that truly opened the floodgates and allowed for the massive scale we see in AI today. So as we finish up here, it leaves us with this really big question. We've seen how brilliant solutions to these problems of position, stability, and speed have brought us this far. So what's next? What is the next great barrier that AI needs to overcome? Whatever it is, you can bet the solutions will be built on the very foundations we've just explored.